of a complex number. So we've done both of these before, and we will talk about argument using a manual process, and we'll also look at how we can use our calculator to do it as well. So firstly, what does modulus mean? It just means what's the distance, what's the length, what's the size of this complex number, and it is the square root. So we denote it like this, the modulus of z, and it's going to be the square root of the real component squared plus the imaginary component squared. You can see negatives don't have an effect because we're squaring them. It becomes the square root of 1 plus 4, it's the square root of 5. Okay, and we're going to leave it like that. That's a good way for us to leave it. Okay, now we can find the argument just by using our calculator. And we like to express arguments in radians. Alright, so I'll go through that one in a moment. Let's do it manually first. Let's consider a plane, or even a unit circle. And what we have is we're going across 1 and down 2. Across 1 and down 2. Okay, so this is the complex number we're talking about here. Across 1 and down 2. And we want to know the argument of it. Now look at the domain, the restriction for an argument. Okay, we go from negative pi, so that's from here, negative pi, all the way around to positive pi. Okay, so that means our answer here, we're going to find this angle. Alright, and it's going to be the negative angle, isn't it? So I think the easiest way for us to do that is to think about what is this angle here, okay, to determine what this angle is here, and then to take it away from pi. Okay, so if we think about that angle, now I'm going to draw that triangle out. We have across 1 and down 2. I haven't drawn it very well there. That's for this angle. Let's call that phi, because the angle we want to know is theta. Phi. And in order to find I, what we can see is it's going across 1 and down 2. We could go, what is tan, or tan of phi? Tan is O on A. What is tan of 2 on 1? Okay? That's, I think, probably the most straightforward way to do it. Can't see a unit circle here. Sometimes it links to the unit circle, so I haven't set this one up very well. I'll grab the calculator first. So, 2. Yeah, so this is a nasty one. And I've got 1.1. 1.107. So to 3 6 1.11. So that's what phi is. And if we want to know theta, okay, that's what phi is. If we want to know theta, theta is going to be pi, or you can think of 180 degrees, take away 1.11 radians. What is pi? Pi is 3.14. So we've already got an idea. It should be just about 2. So we go pi, take our answer, 2.034. 2.03. Okay, that is going to be the argument. That's the size of the argument. But the other thing we've got to consider is that it's negative. We're going below where we start on the unit circle. So let's answer that. The argument of z is minus 2.03. Okay, so we have the modulus and we have the argument. Let's talk about how we can just use our calculator very quickly to generate the argument. So we're in run that. We'll write this process here. We run that, run matrix, and we press option, complex, option, complex, and R. We want to know the argument of, and then we've got to type in the complex number. So our complex number is minus 1, take 2. I is F1. And we've got the minus 2.03. Okay? So that's definitely the easiest way to do it. And that's the way I'm going to encourage you to do it. Okay? Some of them, if they correspond with the unit circle, you can determine them by looking at it and so forth. But I think let's just jump straight to our calculator. Okay, part 2. We're going to sketch some regions here on the complex plane. So the first one says, sketch the region such that the modulus of z is more than 3. So if we think about the complex plane, and we've got some complex number, but we're saying the modulus of it has to be larger than 3. Alright, so if we were to draw a circle with a radius of 3, okay, our complex number z, because it has a modulus that's larger than 3, it has to be outside of this circle and not touching it because we're not including it. Okay, so maybe we should have a dotted circle that just insinuate, but it suggests that it exists outside of that region. Okay, with a radius of 3. Alright, in B, we're not defining the modulus, but we are defining an argument. It's between pi on 2 and 2 pi on 3. So you can use your unit circle to help you, but pi on 2 is straight up, and 2 pi on 3 is going to be this coordinate here. And so it exists, it's a ray that exists outwards in that direction for all values. We don't have a limited modulus. Okay? Occasionally you'll have both. You'll have a limit, you'll have a ray and a limited modulus. Okay? You might say something like, and that the modulus of z is less than 2. So we could restrict it so that the radius of this arc is less than 2. Okay, let's move on to 3. We've seen this stuff before. So we've got a proof that the modulus of z times the modulus of w is equal to the modulus of z times w. So what we want to do with a proof, we want to start with the left-hand side. We want to try and manipulate it to make it equal the right-hand side. And the very first thing we should do is define z and w. Alright, so that z is going to be some complex number, and w, so I'm going to say let z equal a plus bi, and w equals c plus bi. Okay, so I've defined the two complex numbers. Let's start with the left-hand side. So we have the modulus of z times the modulus of w. That's going to equal the square root of a squared plus b squared times the square root of c squared plus e squared. Okay, using rules of surds, we can collect them under the single root. We can form FOIL. Okay, so we'll stop there because then we'll jump to the right-hand side and we'll see how can we now manipulate the right-hand side to make it match this. We could keep processing here if we know the direction we're going in, but all we need to show is that they're equal to one another. It seems to me that this is going to be the easiest way for us to do it. So this is the left-hand side. Now we're going to consider the right-hand side over here. We've got the modulus of ZW equals the modulus of just perform the FOIL there, VDI squared. Alright, and then what we want to do is we want to collect the real components and the imaginary components so that it's expressed as a single complex number. So the real part is going to be AC take BD. Okay, that's the real component. And the imaginary component is going to be AD plus BC. That's a C, not 9. Alright, so all we've done so far is perform that expansion of Z times W. Now we have the real part of Z imaginary part, real part of ZW, imaginary part of ZW. Now we're ready to find the modulus. Okay? So now the modulus is going to be the square root of AC take BD squared plus AD plus BC squared, all square rooted. We're going to perform this expansion, collect like terms, and we'll see that they're the same.
Should it be AD plus BC?
That one. Good. So now these two are going to cancel, and we're left with A squared C squared, B squared B squared, A squared B squared, and B squared C squared. Good. All right, last one. We have seen this procedure before as well, so just to recap it to you guys. We have the modulus of z plus 16 equals 4 times the modulus of z plus 1. Now what does it ask for? Find the modulus of z. Is that right? Yep. Okay, so what we're going to start with is we're going to square both sides, because what we want to do is we want to try and get rid of the modulus, and we're using this property, okay, because if we square both sides, then we can express the complex number z like this. So we're going to have, I'll just write squared up here, all right, so that we can go straight to the next step, which is going to be z plus 16 conjugate z plus 16. Let's do it slowly. Sorry. We're going to have z plus 16 equals 16 times z plus 1. Okay, so we perform the square. Next, we're going to use this rule. Okay, so if we have the modulus of z plus 16, then we can express that as z plus 16 times the modulus, the conjugate of z plus 16. That's what this one is here. We have it like that, we can express it like that. And we'll do the same to the other side. Now, the conjugate applies to both terms. We can think of it as applying to both terms separately. So what we have is z plus 16 times the conjugate of z plus 16. Now the reason is 16 by itself is not a complex number, and so the conjugate of 16 is just 16. Okay? And then the same is going to happen over here. Conjugate only applies to the complex number. The conjugate of a real number, a purely real number, is just that purely real number. Okay, then we're going to perform this expansion. So we're going to have zz. Okay, z times the conjugate of z. We have plus 16 times z, plus 16 times the conjugate of z, plus 16 squared. What's that? 15 squared, 225.
256.
256. Yeah. Sounds good. zz plus z plus z plus 1. Okay, now we've got a few things we can cancel once we've expanded it to this point. We can see we've got 16z on both sides, and we've got 16 times the conjugate of z on both sides, that will cancel nicely. And here we've got, these are like terms, aren't they? So I might move that over there to keep it positive. So when I subtract it away, we're going to have 15zz. Keep processing. And then we remember z times the conjugate of z is the modulus of z squared. And so we get the modulus of z squared. Alright, so let's make our way through the B.
You know what I want? You can have this one, but the next one. What's the next?